ultimately the whole point of hypothesis tests is to make decisions, and there's a variety of things that can end up happening here. One of which is that our null hypothesis is true, or null hypothesis is false. So that's the binary view of the world. But there's a couple of things that can happen within those two different worlds that will affect our decision here. One of which is that we could fail to reject H naught. In which case, if we don't reject H naught, then H naught is true, then there's no error. Similarly, if we reject the null hypothesis and the null hypothesis is false, then once again we have no error. Good deal, right? On the other hand, if our null hypothesis is true and we reject it, then we have what we call a type 1 error. And if the null hypothesis is false, yet we fail to reject it, we have another error, and that one's called a type 2 error. Right? And alpha is the probability that we have a type 1 error, and that's a fairly universal symbol, and beta is the probability that we have a type 2 error. Again, beta being a fairly universal symbol. One key aspect here is that if we want to minimize these errors, for instance, let's minimize alpha here, that we would end up rejecting H naught except for it was true. Right? Well, it turns out that if we wanted to do that, and we could minimize that, unfortunately we're going to expand the likelihood that we end up with a type 2 error. Right? So we cannot minimize alpha and beta simultaneously. And we'll illustrate that as we get into another example of hypothesis testing situation. Let's look at an example where we have a manufacturing plant of asphalted concrete, and there's a desired value of the asphalt content, which turns out to be 5% in this case. And the engineers know that no matter what the different desired value is, that the plant variation between different batches, that there's a known deviation of 0.75%, deviation in this case being the standard deviation. So the population variation is known, whereas this is for a particular batch going out, or series of batches going out, this is the desired value. So the materials testing engineer must report on the basis of these 3 batches whether or not our sample mean, the average of those that are going out, and whether or not that's going to be within an appropriate distance of the mean, true mean. Right? How representative is this? Is this getting us close to the desired value? So they're going to look at this range here. Ultimately, we're going to start trying to figure out, well, what should that C be under different kinds of conditions. Okay, so let's first go to some sort of a null hypothesis, where, since this is our desired value, that's the design value, so to speak, we'll say, okay, our null hypothesis will be that our true mean or population mean equals 5. And in this case, the alternative will be that it's not. So it's a two-sided type of situation. Okay, now we know that our sample mean is going to be approximately normal with its own mean and standard deviation, and of course we know that that's going to be equal to our true mean, and our standard deviation is going to be equal to sigma over square root of n, or 0.75 divided by square root of 3, since we're using a real small number here, 3 batches, n equal to 3, and that's about 0.433. Okay, so this is what we want to test, whether or not our true mean is really 5, based upon our 3 batches that we're going to take a look at. Right, so our operating rule then is we have to decide how close is close enough. And so if one way that we might form a decision based upon operating rule is that we'll accept H1 if, let's make that, we're going to accept the null hypothesis at the 10% significance level if our sample mean lies within plus or minus c of 5. Else we're going to reject. And that leads us to that we want to choose C such that the probability that X bar is outside of plus or minus C, and now we need some sort of percentage that's acceptable. Well, that's what the significance level is. So there's our 10% number. And since X bar is normal, then we can go right at this in the following kind of way. Right? Probability here that X bar is outside is also could be stated as the likelihood that it's inside. That's 5 minus C, 5 plus C, and that's going to be given our null hypothesis is equal to 1 minus alpha. Right, now note what I just did here was I said alpha was our 10% number, and that's going to turn out to be our significance level, and it's also going to turn out to be associated with our probability of type 1 error, and we'll draw that all in a nice package with a bow here in a second. So that's going to be equal to 90% in this particular case. Okay. Our test statistic is going to be Z equal to X bar minus its mean over its standard deviation, which will be sigma over square root of n. Okay, so for a normal distribution then, this statement here becomes the game associated with the normal, cumulative normal. So we've got a set of normal curves down here below. Let's work with that. What we're trying to do is find out where exactly is it that we're going to end up with an interval where we'll get 90% of the area. Now the two curves we have here, this first one is just our normal distribution on X itself, And notice that as we go to the sample mean in its distribution for n equal to 3, that it gets narrowed up from the outer one to that one. Okay, and if n were to get larger, of course this would get smaller and smaller, still centered right here. So we're really trying to find this region in between what should be plus or minus c, and so we've got this two-sided central area of 90%, so that means 5% out in the tails. Right? So this is really all about the normal distribution. So the cumulative normal CDF, using this guy right here, we'd have 5 minus c, that's where we want to be at the lower bound, minus the mean, that's 5, over our standard deviation of 0.433. Right, so that would, of course, just be 5 minus c over 0.433. Right, and we're going to set that equal to alpha over 2. That'll be the area out in the left-hand curve, that tail, so that'll be 0.05. And that will give us then that we have minus c over 0.433 is going to be equal to minus 1.65 once we look up the z value, and therefore we end up with that c is equal to 0.71. Note that if we change the number in our sample size, we're going to change sigma, and that's going to change c as well. That's important for us to take note of later on. So our interval just became 5 plus or minus 0.71, and that's 4.29 to 5.71. And down here then on our chart, 5.71 is about here, and then 4.29 is about there, and that area will be 5%, that area will be 5%. And what we're saying is that if our test statistic, statistic turns out to be within our region, then we're going to end up accepting H naught. And so this then represents H naught being accepted, right, at the 10% significant level. So let's go back for a sec. We said alpha was our probability of type 1 error, and it's also here our significance level. It's typically equal to 10, 5, or 1%. And presumably, theoretically, you would choose your alpha level depending upon the consequence of making a mistake, as is your type 1 error. Conventionally, though, you typically use the same value over and over, and that oftentimes is 5%. Okay, so, and let's restate this just to really nail it down here, that we're looking at mu plus or minus c here, and 5 plus or minus 0.71. This was our target value, right? and this is coming out of our known population and then dividing by the square root of our number in our sample. And so our rule is that if x is contained in that interval of 5 plus or minus 0.71, then we accept our null hypothesis. Otherwise, we're going to reject. Okay, that's again here a crucial aspect here. Let's say that we always used 10%, right? If so, we would end up being wrong or in error 10% of the time. Right? Sort of like the confidence interval thing, that if we constructed confidence intervals in a specific way, say it was a 95% two-sided confidence intervals, then 95% of the time those intervals would contain the true mean. Not 95% probability that a specific interval contains the true mean, but with that construction technique, we did it over and over and over and over, 95% of those would contain the true mean. And it's sort of the same way. If we follow this procedure over and over and over and over, using this 10% kind of idea, then we'll have we would only end up being wrong 10% of the time. And being wrong means we reject our null hypothesis when it was actually true. Okay, and that is the very definition of our type 1 error. Look at this in terms of some additional data here. Now we've gone and we've actually done our test, and we sampled from 3 different batches, and here are our values for the asphalt content. And here it's pretty easy to tell that with n equal to 3, our x bar is equal to 4.2. And 4.2 is outside of our threshold value of 4.29 to 5.71, and therefore we would reject H naught, that the true mean was equal to 5. Now you get an interesting set of issues if this sample mean was 4.25, 4.28, or 5.72, or how close is close enough is a valid question to ask. Once again, you have to sort of make a decision about how you're going to handle that, creating an operating rule that is about how you're going to handle that. Okay, so note if we make alpha too small, right, that's going to broaden out our interval, right? So we could actually get the 4.2 in there if we do that. But if we make alpha too small, we end up increasing beta. That is, that we're going to end up accept HO, or really fail to reject HO, when we should have And so that's our type 2 error that we're concerned about. Right? And to get into this in a numerical way, we have to start posing hypotheses. Excuse me, we have to pose scenarios, do a slight parameter kind of variation here. So say the true mean equals 4.5. Now I know that number seems quite arbitrary. Right? And so you have to sort of play a little bit of a game here. It's a parameter variation. You're going to see in just a second that we're going to look at this for a whole lot of different possible values here, but we're going to choose one at random just to show how you might do this. Okay, so if the true mean were actually 4.5, right, and that means we should have rejected the null hypothesis, which said that the true mean was 5. Right, beta is this chance that we're going to make an error. Right, so beta equals probability that our sample mean is between our bounds, and yet for this specific case mu is equal to 4.5. And we're interested in what is that number. Well, once again we're back into normal distributions here, right? And so our upper number here is Z2 equals 5.71 minus our new mean of 4.5 divided by 0.433. That hasn't changed. Right, so that's about 2.8-ish and change. 2.80 if you carry out enough digits. And Z1 is equal to 4.29 minus 4.5 over 0.433, and that's about equal to a negative 0.5 or 49-ish. Right? And so now when we go look at this on our chart, note that because the mean is different, the true mean is different, so we've shifted the curve over a little bit. Right? So we're still going to look at areas that are associated with 4.29 and 5.71, right? But it's going to be a different area than what we were working with before. Right, now that's the one we want. That's our beta, right? Probability that our sample mean turns out to be in the range rather than outside. Now while we're right here, I want to point out something, that the power is this other area. So power equals 1 minus theta. We'll come to that again in a second, but it's so nicely illustrated right here. And for this one, we go look up our appropriate z values in the normal distribution curve, and so we get our cumulative evaluated at 2.8 minus our cumulative evaluated at minus 0.49. Notice we can't do any fun 2 times things here because these numbers are not symmetric with respect to the standard normal distribution, right? And so that will be about 0.998 minus 0.314, and we get then beta equaling to 0.634. So a 63.4% chance for the case that mu is equal to 4.5. Right, now we could do this for a whole variety of mu's, an infinite number of possibilities. Right? And so that's what we've done over here, is that for n equal to 3, we've now computed what beta would be as a function of all these different true means. Okay, so our value of 0.634 was at right here at 4.5. That's where we got one of those, and then we repeat that whole exercise for all whole other kind of wide range. And notice that it peaks out at 0.9 right here at our original mu equal to 5. We could also run sort of a theoretical in our minds. What if we increased and doubled, in this case, the sample size? What happens? And of course it narrows up a bit. Now the thing of it is here that you got to always keep in mind that, yeah, okay, you could increase your sample size, but that has a resulting cost, right? This curve that we plotted of beta versus the true mean, it's called an operating curve, and we're going to be coming back to that in a little bit later. And then you see down at the bottom of the page here another statement that the power is equal to the probability of correctly rejecting a false null hypothesis. That's kind of a useful sort of concept, right? That we not only are interested in correctly accepting the null hypothesis, but we're also interested in the probability of correctly rejecting a false null hypothesis. And again, there's this whole notion that you have to somehow balance between alpha and beta. You drive beta down, you drive alpha down, drive the type 1 error probability down, you're going to increase the error of a type 2. And so you have to balance between those two. And again, by convention, we tend to fix our, you can fix the alpha value, and then it's a little bit of playing around of, well, what sample size might I use to optimize what the beta probability is going to end up being, and balancing resources as a result. You also have to balance what the consequences are that also go along with ending up in either an alpha or a beta type situation, or type 1 or type 2 kind of error.